So in the previous video, you saw how the patterns of stars will change both in time as stars move around in our galaxy, and you could look at the constellations many thousands of years into the future and many thousands of years into the past. But you also would see the stars appear to have different positions if you looked at them from different locations in our galaxy. In that previous video, there was a simulated fly around of the Big Dipper, and you could see how the stars in the Big Dipper change their positions if you look at it from different perspectives. Another motion of stars in the sky that we can see is an apparent motion that forms pretty pictures of star trails. As the night progresses, stars will appear to move across the sky. Now, in actuality, it is not the stars themselves that are moving, it's the fact that the Earth is spinning and we're attached to the Earth, so we're going along for the ride. But from our perspective, if we think of ourselves as stationary, we could think of the stars themselves as all spinning around us as the night progresses. So, here's a very pretty picture of some star trails. If you want to take a picture of some star trails, you set up a camera, you leave the camera shutter open for some number of minutes or hours, and as the Earth spins, the star trails will then appear on your camera. So, knowing what you know about the rotation of the Earth, can you estimate the duration of this photo? In other words, how long was the camera shutter open for? Take a moment, think about it, pause the video if you need. I have a hint that I'm going to give, and then we'll talk about the answer. So, as a hint, pretend that the sun never rose, because we want to imagine that we could see the stars at all hours of the day or night. If you were to leave a camera shutter open for one full day, what would you expect the star trails to look like? Well, in other words, how long would it take a star to make one complete circle? If the Earth spins on its axis every 24 hours, then you would expect a star to make one complete loop in 24 hours. So to solve this question, let's find a star that we'll just track. So I'm going to pick this star trail right here. So the star trail appears to begin right here, and it appears to end right about here. It kind of right away collides with another star trail, but if you look closely at the picture, you could tell those are different stars. So this is the star trail I'm going to track. And then I could ask the question, if one complete loop is 24 hours, this is not one complete loop. So what percentage or how much of a complete loop is this? Well, 1/3 of a complete loop would be about 1/3 of a day. So that would be about 8 hours. So how long is this star trail for? It appears to be about 8 hours. If I want to be more precise, I could just copy this arc that I drew in PowerPoint. I could add it 2 more times, and I still have a little bit left over. So I could say this arc is a little less than 1/3 of the way around. So let's say this star trail represents about 7-ish hours in time. So I could estimate that this camera shutter was open for about 7 hours, give or take. The length of the star trail, or another way of phrasing that, the angle of the arc that the star makes in a star trail, will depend on how long the camera shutter is open for. 20 minutes, about 1/3 of an hour, so about 1/3 of 1/24 of the entire day, you get about only a very short star trail. 1 hour, about 1/24 of the day, you get a longer star trail. 3 hours, that's 1/8 of the day, you get an even longer star trail. So, as another question, thinking about star trails, thinking about the Earth, the picture of the celestial sphere, can you approximate more or less where on Earth this picture was taken from? Well, if we look closely at this picture, we see some star trails going around here. So this is going to be one of the celestial poles, but we see some star trails go around the other celestial pole as well. So this location is probably somewhat kind of close to the equator, because we could very clearly see star trails going around both celestial poles. This image was taken from Mount Kilimanjaro, which is only 3 degrees below the equator. And in this case, you could see star trails going around the south celestial pole, and the pole is barely above the horizon. The Earth spins on its axis, and the Earth spins once every 24 hours. So, one complete day is the time it takes the Earth to spin on its axis. Because of the Earth's rotation, objects appear to us to rise in the east and set in the west. Now, again, especially for the stars, it's not that the stars are moving in any significant manner from our perspective. The the motion of the stars is apparent to us due to the fact that the Earth is spinning and we are attached to the Earth going along for the ride. Two other ideas that we will be coming back to in the next two sections are the idea of the celestial equator and the celestial poles. So, to envision the celestial equator, picture that you were to take Earth's equator and then just bring it out, stretch it, and project it up onto the sky. And that will be the celestial equator now. Similarly, for the celestial poles, you could take the North Pole and the South Pole and project them up onto the celestial sphere. So the South Celestial Pole is the location on the sky directly below the South Pole of Earth, and the North Celestial Pole is the location on the sky directly above the Earth's North Pole where celestial Santa Claus lives. As night progresses, if you think about it, the stars will appear to move around the celestial poles. This is what we saw in this picture here, and even more dramatically in this picture here. It's the Earth is rotating, and the Earth is rotating about its axis. So the Earth is spinning around its axis, which goes right through the poles. But from our perspective, we imagine ourselves as being stationary and we see the stars moving around. But the stars are going to be appearing to move around the celestial poles. So this is again just an apparent motion due to the fact that we're attached to the Earth and going along for the ride. In addition to the 24-hour period of the Earth rotating, there's another motion of the Earth known as precession. The Earth is tilted, and we are going to talk in the next chapter that this tilt is largely responsible for the seasons, summer and winter, spring and autumn. Now, from one day to the next, the Earth's axis is largely unchanged. The Earth's axis is just the line. Here's the north axis and the south axis, and the Earth spins once every 24 hours about this line. And however, over thousands of years, the direction of the Earth's axis is going to be changing. Right now, the Earth's axis happens to be directed and pointed almost perfectly at the North Star Polaris. So that's why Polaris is the North Star. But this is not always going to be the case. Over thousands of years, the Earth's axis will sweep out a circle. So in this animation below, you see the Earth going through a 24-hour period of day-night, spinning around its axis, going really fast. In addition to that motion, you also see the Earth's axis slowly sweeping around a circle. And it takes 24 hours for the Earth to spin around its axis. It takes about 26,000 years for the Earth's axis to make one complete precession, one complete loop around this circle. Right now, as I said, the Earth's axis is almost pointed at the North Star Polaris. In about the year 2100, the Earth's axis will be even closer to Polaris, but then it's gradually going to move away from the star Polaris. And 12,000 years from now, the Earth's axis will be pointed very close to a different star, the star Vega. There are going to be other stars that the Earth's axis is going to be closer to, such as Aldebaran and whatever this star is, Alrai, even sooner. But Vega is notable in that it's one of the brightest stars in the sky. It's something like the third brightest star visible to the naked eye. Polaris itself is not the brightest star by any means. It's probably about the 45th brightest star in the sky. but Polaris happens to be very close to the North Celestial Pole now, so it is notable and interesting. 5,000 years ago, during the time of the ancient Egyptians, the Earth's axis was almost directly pointed at a different star. The Earth's axis 5,000 years ago was almost pointed at the star Thuban, way down here, which is not nearly as bright, but much closer to the North Celestial Pole than Polaris is today. Now, we introduced the celestial sphere by first talking about latitude and longitude, and I really want to emphasize that fundamentally, latitude and longitude are just a way of measuring angles on a sphere. The sphere we were talking about there is the Earth. The reason I want to bring that up is it's possible to talk about the celestial sphere and the separation between locations on the celestial sphere in terms of angles. Remember that one full circle is 360 degrees, and by that convention, I could say then, okay, if one full circle is 360 degrees, then a quarter of a full circle will be a quarter of 360, which is 90 degrees. 1/360th of a circle will be 1 degree. Why do we use 360 degrees as a base unit for angles? Why do we use that number? The reason is 360 numerically divides very nicely into a lot of numbers. 360 will divide neatly into by 2, 3, 4, 5, 6, 8, 10, 12. The number 360 numerically is very nice to work with, so that's why a full circle is 360 degrees. You could think about the apparent separation between objects on the sky, the apparent separation between objects on the celestial sphere in terms of angles. So let's say we have a North Star right over here, and then let's say we have some star right on the celestial equator. I could say these two stars are separated by an angle of 90 degrees. And if I say there's a star here and a star here, I could say these two stars are separated on the celestial sphere by 15 degrees. Now, I'm not making any statement about how far apart these stars that I'm referencing actually are in reality, in nature. I'm only making a statement how close or far apart they are appearing to be on the sky. Because again, remember, the celestial sphere is not actually the way nature works, but it is a useful visual tool for thinking about the separation between objects. Very often it will be common to talk about objects that are smaller, have an angular separation less than 1 degree, and astronomers divide 1 degree into arc minutes and arc seconds to describe fractions of angles. 1 degree could be divided into 60 arc minutes, and 1 arc minute could be divided into 60 arc seconds. So 1 arc second is a really teeny tiny angle. 1 arc second is about the limit that the best telescopes on Earth could resolve. So this is kind of like saying 1 hour could be divided into 60 minutes, 1 minute could be divided into 60 seconds. Between seconds, minutes, and hours, a second is the smallest increment of time. 1 arc minute is the smallest increment of angle. Again, a degree, an arc minute, and arc second are just a measure of an angle. In addition to the separation between objects, angular measurements could also be used to describe the apparent diameter or the apparent size of objects on the sky. The full moon is about half a degree across. If I were to look at the moon and I say this edge of the moon to this edge of the moon is about half a degree across, where 1 complete circle is 360 degrees, a right angle will make 90 degrees between the horizontal and the vertical, and the full moon is about half a degree. And half a degree, well, if 1 degree is 60 arc minutes, I could just as equivalently say the full moon is about 30 arc minutes in diameter. The Andromeda Galaxy, on the other hand, is much bigger than the full moon. It's about 5 degrees across on the sky if you were to photograph it containing the arms of that galaxy. It would be really nice if we could see it, but the arms are so dim that we can't see them with the naked eye. So we could see the fuzzy core of the galaxy with the naked eye, but this appears much smaller than the full moon when you're seeing it. Now what I'm going to do to finish off this section is I'm just going to briefly talk about a few definitions that are going to be mentioned. I don't consider this slide terribly important for this course, but a few times these words will pop up, so I'm just going to bring it up. The zenith is defined as the point on the sky directly above you. And you are important here. The zenith is from your perspective. So the zenith is based on where you're standing on the Earth. And if you and I are on different locations on the Earth, we will have a different zenith. Zenith just means directly above you. And the nadir is the point directly below you, so directly opposite the zenith. Now, the horizon is always going to meet the celestial equator directly to the east and directly to the west of you. If you feel very motivated, you could draw a picture out and prove this. I'm not going to really worry or consider this to be too important, but it is a neat fact and you could think about it. The picture is kind of drawn right here. A meridian is a line that is drawn across the sky from the north celestial pole to the south celestial pole, and a meridian runs directly over a line of longitude on the Earth. So that's kind of why sometimes lines of longitude are interchangeable with the notion of meridians. And something I am going to prove on the board in the next video is that the angular distance from the north celestial pole to the horizon will always be the same as your latitude if you're in the northern hemisphere. So the angle between the horizon and the north celestial pole always equals your latitude. The final idea I'm going to talk about is the concept of circumpolar constellations. Now, circumpolar constellations depend on your latitude. Where on the Earth are you looking at the constellations from? And circumpolar constellations are defined as constellations that never set below the horizon. They are always above the horizon. Now, this isn't to say you might not always be able to see them, because if you're looking during the day, then the sun's out, you can't see the constellations. But when the sun sets, you will be able to see them because they never go below the horizon. So as a question, if you want, you could think about the picture of the celestial sphere we have right here. Where on Earth would you need to go to see the most circumpolar constellations? Or equivalently, I could ask, where on Earth would you need to go to see the most circumpolar stars? So you could pause the video, think about this question, and then we could talk about it. Okay, so where on Earth would you need to go to see the most circumpolar stars? Let's pretend I am standing on the equator. So I'm going to be right here in Africa. Now, let's pretend that the sun is over here. So I'm on the equator in Africa and the sun's directly overhead. Okay, right now I cannot see any stars because the sun's out, it's day. But then the Earth is going to spin on its axis. 12 hours later, I will be over here and it will be midnight. The sun is still over here. And at this point, when I'm standing here, I could see all these stars. But then 12 hours later, noon of the next day, all these stars are going to be below the horizon from my perspective. So if I'm on the equator, there will be no circumpolar stars. Everything will rise and set below the horizon. Let's consider if the opposite. Instead of being on the equator, I'm going to go to the North Pole. Now, if I'm on the North Pole, the sun, let's say the sun is right here. The Earth spins on its axis. This star right here is going to just go around this entire loop. And this star right here is going to go around this entire loop. But this star is never going below my horizon. So if I'm at the North Pole or at the South Pole, you have the exact same argument, I will never see any stars set below the horizon. So where on Earth would we need to go to see the most possible circumpolar stars or circumpolar constellations? We would want to go to the North Pole or the South Pole. If I take pictures of star trails as they travel around the celestial poles, in Alaska, almost all the stars are going to be circumpolar because we are very close to the North Pole. If I'm somewhere in North Florida, I will have a few circumpolar constellations, but not too many because Florida is much closer to the equator than Alaska. And if I go even closer to the equator, within a few degrees of the equator, I have hardly any circumpolar constellations at all. So that ends this unit. I'm going to, in the next video, go on the board and prove that the angular distance from the North Celestial Pole to the horizon is always going to equal the latitude. And then we'll begin the next section in the following video.